Hello everyone, I'm Milad Salem. I will be talking to you about confidence calibration for convolutional neural network using structured dropout. Okay. So to give you an overview of what I will discuss, I will go through the usuals, introduction, motivation, related works methodology results, and also discuss what the results mean. And in the end, I will give you one other bonus idea to think about. We have to talk about what is confidence, what is uncertainty. In deep neural networks nowadays, when you train and you get a prediction, the prediction is usually highly confident, meaning that the dropout value is really, really high. You cannot take dropout as a measure of confidence, even if the data has never been seen before. The neural network is really sure that this is definitely a cat, even though it can be wrong and it has never seen such a thing before. What dropout is a technique which I will go in deeper. An MC dropout, multi-corollary dropout, is an approximation that I will also talk about later. And in this work, they take this confidence and dropout and relate it together in the form of an ensemble of networks. Okay, so the idea is that dropout works as if there is an ensemble of networks working. So what's the motivation? If, for example, you have this initial data, if you have this initial data points, two classes, and you want to classify them, a normal neural network would have a really high confidence outside of the boundary of classification. So even if it has never seen a data over here, it's 100% confident that it has to be red, or the vice versa. Which is bad. You have never seen this data, so you cannot be sure which class it belongs to. Something much better would be similar to the other figure, that for the data that you have seen, you need to be confident. You need to have yellow, 100% sure. For the rest, you shouldn't be that much confident. So that's something that we really need. Why do we need this? For example, in many fields, well, this will be harmful to applying your neural network to help decision making. For example, in biomedical domain, if you need to know if a certain part of, for example, an MRI is a tumor or not, you need to know if you can rely on the answer or not. If the answer is 100% sure, even though it's wrong, it's really bad. It will affect your decision making and can have really irreversible consequences. So what is dropout from the start? When you have a network and the data goes through this network, you can sometimes block these nodes inside the network. These nodes don't have to be specifically point neurons as shown here. You can block these nodes and make it so that the data is flowing through a specific subnetwork in your network. This is called dropout. You are dropping out different parts of the network. So what's the Monte Carlo dropout? It is using dropout at test time. If it's traditional dropout, you don't apply dropout at test time. You have dropout during training, and then you just use that to have a better network, more generalizable network. And then at test time, you let all the neurons work. But Monte Carlo dropout is saying that, okay, at test time, I will block out different parts of network, like 10 different ways, and I will show this image of a cat to the network. Or I will show this image of a digit, for example, to the network. In these 10 different instances, I will get 10 different predictions with 10 different softmax values, softmax outputs. Now, if you look at the first image, for example, this is a digit classifier. This kind of looks like a 1, so it is, the predictions are really close to 1. If you look at, if it slanted a little bit more, the predictions are coming down. The 10 predictions that we have are not as sure as they were. And if you look at the middle of the, spectrum, when the angle is too steep, it's not sure anymore. The distribution is completely how do you say, the range has become more, the range has been extended. It means that I'm not sure. Here, I was really sure the 10 predictions were all in the same place. Here, the 10 predictions are all over the place, and I'm not sure what the digit this is. So you can kind of use this and interpret these outputs as samples from a probabilistic distribution, and say that, okay, if these samples are coherent in the same place, then my network has high confidence. If no, they're like this, then my network is not as confident as the other samples. That's Monte Carlo dropout. Aside from that, dropouts can also have different ways to be applied. For example, this is density, for example. You can be dropping only one channel. Inside each layer, you can drop one channel, one filter, just drop that. You can drop a whole layer, which here we call drop layer, or you can drop the whole block. Because it has residual connections, you can drop the block completely and don't worry about anything. So you can drop different things. These are called structured dropouts. Normal dropouts, you drop randomly. But in here, you drop, if you drop, for example, if you choose to drop a layer, in drop layer, you drop the whole layer. In normal dropout, you just drop a few filters. So another thing that is related is deep ensemble that we need to go through before we realize how all these relate to. So this deep ensemble is saying that this is not related to dropout yet. If you have multiple deep neural networks and you train them and then you test them, you will have different predictions and you can apply confidence. You can measure confidence from these many predictions. If, for example, you show a picture of a cat and 70% of the time you get cat and 30% of the models are saying that's a dog, you know, you are 70% confidence that it's a cat. Okay, 70% confident that's a cat. In here, it's showing that well, this is just a toy regression. And in here, for example, we have multiple models, as 5 models have been trained, and you can see that there is a confidence range for the points, for the data points. If you train with adversarial samples, you get more confidence around the data points that you have seen, and a good deep ensemble would show something like the last picture, where in the data points that you have not seen, you're not that confident. The range opens, the range widens. So let's see what they say. They say that let's use MC Dropout and view it as an ensemble. Let's view it using different predictions as using different models. What they say is that, okay, the probability that I will get this output is the same as average of the probabilities of different models with different weights, different WFTs. So it's like saying, okay, I have different weights. It's like different models. I want to get an average of them and get the same output. Okay, it's basically saying that you can treat it as an ensemble. Signed up.
I have another account. Let me see. It's automatically. I have another one. Zoom, but maybe automatically sign in. No, it's sharing. Still sharing.
So, any questions up until now?
Yeah, okay, continue.
We can discuss if you have any questions.
Yeah. At the beginning, you said with like traditional models that the dropout value was really high, suggesting overconfidence. Are you referring to like the softmax value of the prediction is?
Yes.
Or?
Although, like I said, that's not a good measure for confidence.
Yeah.
Because softmax output can be 51, for example, and it's a really good data point that we have seen, or it can be 99, and it's something that.
On the new board, I say, this measure is board is You have to show why it is relevant.
True.
I don't want to discuss. We can discuss.
Sure,
it
sure,
now.
sure, sure. Mhm.
This one.
Okay. Okay. So let's continue. Model ambiguity is defined as what each specific model is saying compared to what the average of the models are saying. What is the consensus and what is each model saying? So if you have a lot of different answers from those 10 predictions, it's too ambiguous. So what they arrive at is that this calibration error, that is the point of this confidence calibration, can be defined as these 4 terms, and these two first terms basically means that if the model is more diverse and the ambiguity is less, meaning that you are getting an accurate result, you will have better calibration. Okay, this is basically what they arrive from the first 2 terms in this equation. Yes?
I guess the way that they're defining ambiguity is that, like, that's kind of the variance, right?
Barrier?
This is the variance in the
Yes.
predictions, right? If
Yes.
the variance in the predictions are high, you're saying it's ambiguous.
Yes.
It's like ambiguous, otherwise it's just confident, right?
Exactly.
But how does that supposed to solve the problem that you started with? So you said that there are sometimes cases that there's an unseen data, but the network is pretty confident and it shouldn't be. How does that gonna address?
True. I think look at it from how accurate it is, that this h of x, the big one, this h of x is the average of the model. Like I have 10 models, and on the average, they're saying that it's a cat. Okay, but I also have, for example, 5 models that are telling different things, compared to I have only 1 model that is saying different class, predicting different class. Okay, if the more models that are disagreeing with the common prediction, the more models are disagreeing, it means we have more ambiguity. So your question is coming from, okay, how about unseen data? I say it's not trivial to know from these measurements. I don't think it's trivial to say that if it's unseen data, we'll have more ambiguity. I don't know, to be honest. I don't know if we can say that, because maybe it's unseen data, we will have more disagreements between the models. You know, if there's a data that's close.
You can say that because it depends on the decision boundary. So, like the first figure that you showed, the green and red, if the unseen data is on one side of that decision boundary, most probably most of the models will say with a high confidence that that's going to belong to red.
Okay.
So the only time that I suspect that like different models give different outputs is that it's close to boundary. So still, it's not clear to me how does that metric is gonna.
But keep in mind the boundary is different for different models. This is 10 different models.
It's not that different.
That's the whole point. They're saying that it's different. They're saying that the result is showing. Okay, so we arrived at this. The whole point is that we have deep ensemble on one hand that has different initialization. This deep ensemble, as I said, is 10 different models. It's not just one model. We have deep ensemble on one hand that has different initialization and results in 10 different models, and we can get the average of those predictions and say how confident we are. We also have a structured dropout that is promoting diversity inside the subnetworks of the network, which can be viewed again as a separate model. And we can again apply average on the predictions of these subnetworks and arrive at confidence. So why not compare them? This is a simple idea, which was not explained like this before, that it is really intuitive, that why not view dropout as an ensemble maker, that inside one network, you are making different ensembles. That's the whole essence of this paper. Okay. So let's compare it. Let's compare a model deterministic without dropout with a model that has the traditional dropout, with the models that have these 3 different structured dropout that we discussed, and deep ensemble, which is completely different thing. 10 different models, for example, although 5 different models. Okay, so for SVHN, which is a small data set, they observe that dropout is actually working as good as a structured dropout. So there isn't much to be said over there. For if you make the data set bigger, you can see that deep ensemble is giving much better results. And in the dropouts, we don't have specifically one winner, but the structured dropouts collectively are getting really similar results from deep ensemble. So the point of this is not to find out which dropout is better. The point of this is not to find out if deep ensemble is more powerful or not. The point of this is to compare the results of something that is just dropout to something that is an ensemble, and say that, okay, we are getting similar results to the ensemble, even though we only have one model and we are using dropout on it. Okay, so there also none of these implementations are exactly their own idea. These are different things that have been implemented before, and then they re-implemented. Okay, it's not that they have created drop layer. No, this is just they are comparing things that already exist. Okay, so there is not supposed to be any winner. Yes, please.
These are
Yes. Yes. True. So this is again the same thing. They're saying that the deterministic and the dropout are usually the blue and let me show you. The blue and the orange one are usually really detrimental in terms of accuracy. If you want to get more confidence, you have to give up a lot of accuracy. That's why they are higher than x equals 0. But structured dropouts are usually close to x equals 0. It means that you don't have to give up accuracy for confidence. And also some of them outperform, like they increase the accuracy. As you gain more confidence, you are also increasing the accuracy. Basically saying that you are getting better results with structured dropout. And let's see, let's talk about ensemble diversity. So they find a way to define the number of models within an ensemble. They come up with inter-rater agreements. And they try to say, okay, if I increase the number of models that I have, will I gain accuracy or not? And it's important to see how much accuracy I also gain. Out of the bat, you can see that deep ensemble is getting more accuracy. But of course, that's 5 different models that are computationally expensive and they're getting high accuracy. But for only one network, you can see that the accuracy is rising twice more than it rose from deep ensemble. So if you, for example, increase the number of models inside your ensemble, if you only have one network, you're gaining more accuracy than when you have different networks. Okay, so the structured dropout is computationally less intensive and also gives you a bigger boost in accuracy compared to deep ensemble when you raise the number of your models. Okay. On the other hand, they're also showing that the error is lower for drop block than deep ensemble, which they don't go that much into. Then you have in inter-rater agreement that you want to see how much these different models agree on your output. Okay, so if I apply prediction for 10 times, how much agreements do I have? And it says dropout produces models with larger agreements, hence less model diversity than a structured dropout. Meaning that the models that come out of a structured dropout are more diverse and they have better agreements. Okay, so one thing that they go into that's a little bit different from the rest of the talk is active learning. The whole point of this talk is at test time generalization at the test time. They want to have better accuracy at test time. They want to have better generalization at test time. So active learning is really in need of that. Active learning is when you train a model and you present it with unlabeled new and unseen data, and you want it to learn from it. Okay, so you want to see if it can use this new data to increase its own accuracy. So you train the model once, you apply it to the real world, and in the real world, it just tries to learn more stuff and tries to bring up the accuracy. As you can see, when you increase the number of training samples, the structured dropouts gain more accuracy and can utilize these samples better, meaning that they have better generalization. Okay, so it's a small thing, but they have better generalization. Okay. So this talk, this paper wanted to reinterpret the Monte Carlo dropout as ensemble averaging strategy. It wanted to talk about this calibration error in terms of diversity of the model, which hasn't been done before. It also showed that structured dropout is giving better results. It's promoting model diversity, and it's improving calibration. And it's showing that there is a gain in performance, but it's really dependent on where you're using it, how you're using it, and what data set it is. It's not a definitive answer that, hey, this dropout is better. This was not the goal of this work. It was just saying that, hey, let's look at dropout in the eyes of an ensemble. That within one network, you are making ensemble of sub-networks. Okay, so I have a few points that we can discuss, and then you can ask questions. The first one is, how does dropout relate to pruning and lottery ticket that we saw before? The second one is, can structured dropout and neural regeneration be compared? That we talked again before. And from these two discussions, is structured dropout enough to be done or not? Thank you. Any questions? And also, if you can please answer these, that's amazing.
They were expecting you to answer. These are good questions. Actually, this can stay here. Just let me.